Welcome to this video on rate laws. A rate law is just a way of us trying to understand how quickly a reaction goes as a function of concentration. And so the way I like to start with rate laws is to give you my very favorite generic chemical reaction. A plus B, so reactants of some kind, make C plus D, products of some kind. Now the capital letters are going to mean chemical identities, so chemical compounds, and I'm going to use lowercase letters for coefficients. This is just a generic way of representing a chemical equation that you'll see a lot in your books or in notes or things like that. And we've been through this before, that we can define the rate of a reaction as essentially concentration, change in concentration, delta for change, over change in time. So there's rates of disappearance, right? We could define the rate of reaction as the rate of disappearance. So the change in concentration of A over time, T for time, or the change in concentration of B over time. Now, these are reactants, and so there's less at the end than at the start, and so we want to make rates positive, so we use negative signs. And if we needed to set these equal to each other, we have to think about the coefficients. A disappears at a rate of little a molecules, coefficients. B disappears at a rate of little b. And so we would need a 1 over A here and a 1 over B if we wanted to make these things equal. We could also define the rate from the rate of appearance, right? So instead of watching the reactants A and B disappear, we could watch the products C and D appear. And again, it's just change in concentration over change in time. And if we wanted to make these equal, I don't have to change the sign this time. They can stay positive because there's more product at the end than at the beginning, so that gives a positive number. But I would, if I wanted to set these equal to each other, have to use 1 over the coefficients so that I was able to say that they're equated to each other because they disappear in different numbers of molecules at a time. So again, what we're seeing here are ties between rate and concentration. And that's true, right? Rate is dealing with concentration. It's also concentration versus time. Those are helpful pieces to us. We're going to look more, especially at this relationship, later. For now, I'd like to concentrate on a way to tie the rate to the concentration of a substance. And to do this, we're going to develop what are called rate laws. So all a rate law does is it ties reaction rate, so that delta concentration, delta time, to concentration. And generally when we're saying concentration, it's reactant concentration. So in my favorite chemical reaction, A plus B makes C plus D, a rate law would have this constant called K, and that K is there for proportionality. We'll get there later. And A to some exponent we'll call X, and B to some exponent we'll call Y. So this could say, oh hey, if I had 0.1 molar A and 0.5 molar B, how fast could I expect this reaction to go? Well, I'd calculate based off of the exponents X and Y that I figured out, the concentrations that I'd put in, and the K that I would find, and I could predict how fast a reaction would go. Let's give you some examples here. The first example of a rate law on the ground that I want to show you is involving the compound bromomethane, right? CH33Br. And it turns out that this can react with water, and what you end up doing is you put an OH group onto the methane compound, and then you get an H plus out and a Br minus out. What I would like to highlight for you is that the rate law for this has a K in it, right? K is this proportionality constant that just helps us get between concentration and rate, because rate has units of molar per second, and concentrations are all going to be in molarity. So K is going to help us make the units match up. The rate just ends up being K times whatever the concentration of the bromomethane is. You notice the water doesn't actually show up at all. So what that means is that the exponent for bromomethane is 1, right? So we would say that this reaction is first order with respect to, and by the way, W/R/T means with respect to, bromomethane. The water doesn't show up, so that really means that over here, the exponent on the water is 0. Why? Because anything to the 0th power is 1. So this reaction is 0 order with respect to water. I could change the water concentration all day and I won't change the rate. However, because bromomethane has something that isn't 0 for an exponent, changing the concentration changes the rate. And in fact, first order means that if I take the bromomethane and I multiply it by a factor of 2, then I get 2 times the rate. So that's example 1. Here's another example for you. This reaction takes the bromate ion, BrO3-, which reacts with bromide ion and H+ ions. And what you get is 3 bromine molecules, Br2, and 3 waters. This rate law is rate equals K times bromate. And by the way, this is just to the first power. Bromide is also to the first power. And the H+ is squared, right? So this reaction is first order with respect to how much bromate there is, or first order with respect to bromide. So just like we saw before, if I do 2 times the concentration, that would be 2 times the rate. Or if I did 5 times the concentration, that would be 5 times the rate. On the other hand, this reaction is second order with respect to the H+ ion. That means that the rate goes up faster with the hydrogen, right? If I take this concentration and I multiply it by 2, the rate goes up by 2, right, the amount that I multiplied by, to the exponent, right? So the rate goes up by 4. Or if I had 5 times the concentration, the rate would go up by a factor of 25, right? It's the amount that I increased by to the power of the exponent. So that's one thing to know, is that rate affects concentration, and you can know how and why. Another thing that I want you to know is that there's an overall reaction order. And all you do is you add all of the exponents. So this particular one has an overall reaction order of 1 for the bromate, plus 1 for the bromide, plus 2 for the H+. So this is an overall reaction order of 4. So those are our basic terms for rate laws. I hope in all of the cases, though, you noticed that there's no real relationship between the coefficients and the exponents in a rate law, right? Coefficients are the numbers in the reaction to balance them, and the exponents are the numbers for the exponents in the rate law. They do not have to be the same. Sometimes they are, sometimes they aren't. And in fact, the only way to get rate laws is through experiment. If I don't do experiments, I can't just guess at the rate law. And there are 3 types of experiments that we can do, and we'll be looking at each of these in class. The first type is what's called the method of initial rates. Right? And the method of initial rates says, let's do experiments where we measure rate versus concentration. So let's do a bunch of experiments. Let's change the concentration of the reactants and measure the rate, and that gets the exponents. and the K and the rate law. The second option is called the method of integrated rate laws. What do? Well, we measure concentration versus time. What do we get? We get the exponents and the K and the rate law. The third option is through reaction mechanisms. And what we do is we use the reaction route. So the pathway of the reaction, how do we actually get from reaction to reactants to products, to get rate law, right? What else do you think we get? Well, we get the exponents and we get the K. 3 ways of using reaction data. One that involves rate versus concentration, one that involves concentration versus time, one that involves figuring out what kind of compounds, the route, get you to the rate. In all cases, you're going to get the exponents, the K, and the rate law, but just slightly different ways of doing it. And so we'll be looking at those in depth over the next several days of class.